Hi everyone, AB students. This is the um, September 29th exit ticket tutorial, I guess. So today, remember, we focused on power rule. And as well, at the end of the exit ticket, I have two questions on differentiability, which we covered yesterday, but there was no exit ticket yesterday. So I just added two quick multiple choice questions for our topic yesterday. Now, today we dealt with power rule. So the instructions say for each problem, first write each function in a to the x to the ax to the n form. This is basically power rule form, right? Because this makes it easy for us to apply power rule. Then use power rule to solve for the derivative of f of x. Take a picture of your work and submit on the exit ticket assignment on Google Classroom for today. Now, yeah, just take a picture. You don't have to do your work on this sheet or anything. I just expect to see each problem like 1, 2, 3, 4, etc. So first, we're going to rewrite this in a to the x n form. I'm going to just put a different function just so I'm not giving you just straight up answers. Let's say it's 2x to the fourth minus or plus 6x, let's say. Now, f of x written in a to the xn form. You'll notice actually that this is already written in power format. 2x to the fourth plus 6x, we can easily apply power rules to each of these. So I'm just going to say 2x to the fourth plus 6x. If I want to be really precise, I can say 6x to the 1 because that's more in power rule format, right? Power rule is ax to the n, right? So I have the x to the n, x to the 1 here, right? So it's more precise. But in this case, I could also just leave it as 2x to the fourth plus 6x because we can all use power rule for this. Now we're going to find the derivative of power rule, the derivative of f of x. Now remember, power rule is you have x to the n, right? And then if I take the derivative of this, I'm going to get nx to the n minus 1. So I take the exponent, which is n, I multiply it, so I bring it down here, and then I subtract 1 from n. So this is the format we're going to use. So 2x to the fourth, I'm going to bring the 4 down, multiply it by 2. So I'm going to get 4 times 2, x to the 4 minus 1, right? We're going to subtract 1 from the exponent, plus 6 x is to the 1, right? So it's going to be x is to the 1 here, right? So it's really going to be 1 times 6 x 1 minus 0. Or sorry, 1 minus 1. I'm subtracting 1 from the exponent. So this is equal to 8x cubed plus 6x to the 0, which in reality is just 1, right? Because anything to the 0 power is 1. And that's a pattern you're probably pretty familiar with. When you just take the derivative of, say, 6x, you know it's just 6, right? So in this case, we can see that when we apply power rule, we get 6. I just went through all the detailed steps here. And then 2x to the fourth, that's just like, I think, a pretty normal power rule. Okay, the second problem is kind of more difficult because we have to apply 2 of our other rules. So first, I'm going to write them out here that we covered today. We used negative exponent rule. Which essentially says if you have something to the negative exponent, it's equivalent to this, right? So something to a negative exponent, you can bring it to the denominator, and then now it's to the positive exponent. Or alternatively, you can have it, let's say, a positive exponent, and bring it down to the denominator, and now it's a negative exponent. I think I wrote it in, yeah, so like this, right? So the idea always is you just you can flip the side of the exponent, like flip the term with the exponent over a fraction from the numerator to the denominator or the denominator to the numerator, and then you just switch the sign. So in this case, 1 over, oh, sorry, we also have another rule, which is fractional exponent rule, which says a to the m over n is equal to square root of n a to the n. So the denominator is the n, so n is in the denominator, and it's also like the root. And then, sorry, m is in the numerator, and it's also the exponent. So in this case, let's see, f of x, right? It's 1 over the 15th root of x to the 5th. Well, 15 I know is going to be in the denominator, right? So it's going to be 1 over x, 15 is in the denominator, 5 is going to be in the numerator, right? So, but it's all under 1, right? It's all still under 1. So 1x 5 over 15. Now I'm just going to simplify this to 1 over x 1/3, right? It's 5 over 15, so it's also equal to 1/3. Now I notice that this is in the denominator. Well, I can use the next negative exponent rule to bring it to the numerator. X to the 1/3 is positive in the denominator, so I bring it to the numerator. Now it's negative, so x to the negative 1/3. Cool. X to the negative 1/3. Now this is in power rule form because we can find the derivative of this. The derivative of this, I'm going to bring negative 1/3 down. So negative 1/3 multiplied by x. And then I'm going to subtract 1 from negative 1/3. So it's going to be negative 1/3 x minus 4 over 3. Oh, I just realized I did this exact problem for you guys, but whatever, that's okay. Let's see, this next problem, I'm going to switch it up. So instead of 4 square root of x minus 2x, I'm going to do 4. No, let's do 7 square root of x minus 8 over x squared. So I'm going to first use, for 7 root x, I'm probably going to first use fractional exponent rule, right? Because I have a square root, so I can change it to a fractional exponent. So anything that's the square root of x is just going to be to the 1/2. So it's going to be 7x to the 1/2. And you can see this because square root of x is really, there's a 2 here. There's a small 2 hidden here, and then there's a 1 here because it's x to the first power, right? So then if you follow this format, you're going to get 7x to the 1/2. And that's just something you should memorize. Anytime you see a square root of something, it's really just x to the 1. It's just really that number to the 1/2. So like square root of x is always equal to x to the 1/2. Anyway, then it's minus 8 over x squared. Right? Now, minus 8 over x squared, I can bring the x squared to the, so like minus 8 over x squared, I can bring the x squared to the numerator, right? So really, I'm going to get 7x to the 1/2, because that's already in power rule form, minus 8x to the negative 2, because I bring it to the numerator, and then I change the exponent to negative. Sorry for my bad handwriting. Oh my gosh, okay. 8x to the negative 2. Well, I'm not going to, actually, sure, I'll box this. It's our answer for this first part. Just like this, and just like this. Now I'm going to use power rule, 1/2 times 7. So it's going to be 3.5. x, and then 1/2 minus 1, going to be negative 1/2, minus negative 2 times, so this is important. So it's going to be negative 2 times negative 8, right? Because this is negative 8. So it's going to be positive 16 x to the negative 2 minus 1. So it's going to be minus 3. Okay, this final one, I'm going to rewrite this as, let's say, 4x to the 3/7 plus 2 over x to the negative 2/5. Okay, so good thing is this isn't in square root form. It seems like it's already in fractional form, fractional exponent form, so we don't have to we don't want to convert it back to square root. That would only make it more confusing for us. So let's just do the negative exponent rule. Let's bring everything to the numerator. So it's going to be, we're going to bring the x to the 3/7, flip it up here. So it's going to be 4x to the negative 3/7 plus, we're going to flip this up here, right? But this one's a negative exponent, so it's going to turn positive. So it's going to be 2x to the 2/5, right? Sorry, I'm not looking at this problem. Okay, cool. So now it's in power rule format. Let's do power rule to find the derivative. So negative 3/7, we're going to take this exponent, right? And we're going to multiply it by 4. So here, I'll just show my work. Negative 3/7 times 4x minus 3/7. Then we're subtracting 1 from the exponent, right? The same thing with the second term. We're going to do 2/5 times 2, right? We're taking the exponent, 2/5, multiplying it by 2. Then x multiplying by 2, and then we're subtracting 1 from 2/5. So 2/5 minus 1. Now, negative 3/7 times 4 is going to be negative 12/7. X, so that's it, minus 3/7 minus 1. So that's going to be negative 10/7, right? Because we're subtracting 7/7. So negative 3/7 minus 1 is negative 10/7 plus 2/5 times 2 is going to be 4/5. X negative 3/5. 2/5 minus 1 is negative 3/5. So this is going to be our answer. Awesome. So I basically, for this part, I just want you to fill out this chart, however you want to organize it. Next, we're going to look at some differentiability problems. So which of the following functions are differentiable at 0? So remember, when we look at differentiability, the first thing is to remember is that differentiable means we can take the derivative of the function at that point. So again, if a function is differentiable at a point, that simply means, the only thing it means is that we can take the derivative of it at that point. The derivative exists, basically. It's a thing. There are times, for example, when there's an asymptote where there's a discontinuity, you just simply can't take the derivative. So that means it's not differentiable. Now, to find differentiability, we can do it in two different ways. We can look at it graphically, right? Remember, at discontinuities, there's no differentiability, right? So if the graph is like that is not differentiable. You have sharp corners, that's not differentiable. And what else is there? Vertical lines, so vertical slopes. So like this, right over here, there's a vertical tangent line that is not differentiable. And then also we can do it through derivatives, which is, I would say, the more mathematical way of doing it is just calculate for the derivative. So this first problem here, which of the following functions is differentiable at x equals 0? So let's see if we can find the derivative. So the derivative of absolute value of x at 0, to be honest, that's not something I have memorized, the absolute value of x, right? Like, what's the derivative of that? What is the derivative? It's kind of confusing. So this would be one I would recommend thinking about graphically, because the absolute value of x graphically just makes a lot of sense, and it's easy to see what the answer is. So x is like this, right? And then the absolute value of x is like, it's this whole thing, right? So the absolute value of x, there's clearly a sharp corner right here, right? And at sharp corners, we cannot find a derivative. So it is not differentiable at x equals 0. Next, we're looking at the cube root of x. So this is really, remember, we can do power rule, but we have to change it into our form first. So it's x to the 1, so we're going to put the 3 in the denominator, 1 in the numerator, so it's x to the 1/3. Now let's do power rule. So f prime of x is equal to 1/3 x minus 2/3, right? I bring the 1/3 down, and then I subtract 1 from the exponent, so negative 2/3, which is really equal to 1/3, and then I bring the x down, so it's x, I'm using a negative exponent rule, x to the 2/3, right? Because I brought x to the negative 2/3, I flipped it over to the denominator, so now it's positive 2/3. Now let's plug in 0, f prime of 0 is equal to 1/3 times 0 to the 2/3. 0 times 2/3 is equal to 1/0, right? 0 multiplied by anything, the exponent of 0 to the 2/3 power 0 multiplied by 3 is also 0. So this clearly doesn't exist, right? This derivative does not exist. What's 1/0? It just doesn't make sense. So it's also not differentiable at 0 on the second one. Now let's look at x cubed. Well, the derivative is, let's just do power rule, and that should be pretty easy. It's just 3x, right? You take the 3, multiply it down, you bring it down, so it's 3x, and then you subtract 1 from the exponent, so it's 3x squared, right? Let's find this at 0. F of 0 is equal to 3 times 0 squared, and that's just equal to 0. Well, 0 is actually a number that exists, right? That's not impossible. So that's totally fine. It could be 0. It just can't be 1/0 because that number isn't real. So this one does exist. So the answer is going to be C, 3 only. Okay. This next problem is, if f of x is continuous at x equals a, which one of the following must be true? So the definition of continuity, I think it might be helpful to remember, is that the limit as x approaches a of f of x is equal to f of a. And what this is really saying is that as the limit as x approaches a of f of x is approaching f of a, it is equal to f of a, this is really saying the two-sided limit, right? Remember, for the limit as x approaches a, for that to exist, it's really saying the two-sided limit also exists, and it must be equal to each other. So the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x, and this must be equal to f of a. Right, so it's saying, like, let's say I have a graph here, and for it to be continuous, the limits from the left, right, from the left and the right must be equal to each other. Cool, so that's marked off. And it must also equal f of a. It must also equal the actual value. And it is in this case, because this, what I drew, is continuous. So that's also great. Now, the first part, the limit as f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right. Well, that's what we just discussed, right? For this to be possible, this must be true, right? For that to be possible, the two-sided limit must equal each other. So this is true, right? Now f of x is differentiable at a. Well, we're talking about continuous, right? We said that for a function to be differentiable, if it's differentiable, it must be continuous, right? That's what we said for differentiability. But here we're saying if it's continuous, does it have to be differentiable? And that's not true, right? So if it's a differentiable function, it has to be continuous, right? So it's like that one Venn diagram I drew in class, right? Or I didn't draw it in class, but it was in our notes. Here's all the continuous functions, right? And here's all the differentiable functions. So if it's differentiable, if I'm in this circle, I'm automatically continuous. You'll notice like I'm in this bigger C circle, right? However, let's say I'm continuous. I might be differentiable, right? I could be in this D circle, but I could also not be differentiable. So the second one isn't true. I don't have to necessarily be differentiable at x equals a. For example, I drew earlier the absolute value graph. This is continuous. You notice I didn't pick up my pen, right? Yeah, I know it's not differentiable because there's a sharp corner. So 2 is not incorrect. F of a exists is a third one. Well, let's look at our definition. What happens if f of a doesn't exist? If f of a did not exist? Okay, it can't be continuous then, right? Because what does this limit of f of x equal to? If f of a doesn't exist, then this whole thing can't be true, right? You don't even have anything to be equal to each other. F of a doesn't exist. So how can the limit of f of x as x approaches a be equal to f of a when f of a doesn't even exist? So f of a has to, at the very least, exist, right? So that must be true. So it's going to be 1 and 3. So it's going to be C also. And that is it for the exit ticket. Just email me if you have any questions, but that's it. Thanks for tuning in.